Satellite imagery datasets, such as those produced from various Landsat sensors, are powerful tools for being able to distinguish amongst land cover and investigate spectral properties. As we've learned in previous lectures, landscape features such as healthy and unhealthy vegetation have different spectral responses. These differences can be captured by satellite imaging sensors and stored within a remote sensing image. For example, the Landsat 8 Operational Land Imager, or OLI for short, sensor acquires spectral information in 9 sections of the electromagnetic spectrum. All 9 pieces of information, known as bands, provide accurate information about how landscape-level features reflect energy across the areas of the electromagnetic spectrum. For the purposes of this tutorial, we're only going to focus on 6 of those bands, which are visualized as the rectangles you see on the spectral signatures chart. The OLI sensor captures 3 bands in the visible spectrum, band 2 being blue, which has a center of 482 nanometers, band 3 green, which has a center of 561 nanometers, band 4 red, which has a band center of 654 nanometers. There's one band in the near infrared, which is band 5, which has a band center of 864 nanometers, and then there's 2 bands in the shortwave infrared section, band 6 being around 1600 nanometers, and band 7 being around 2200 nanometers. Let's start by looking at an example of a Landsat scene. This image over a portion of Vancouver, Canada is comprised of 6 individual bands. Each band has the same number of pixels with the same spatial resolution over the same area. The only difference is that each band is showing the spectral reflectance from its corresponding wavelength range. Each band by itself is panchromatic, displaying information from black to white. This means that our Landsat scene is actually a grouping of 6 different panchromatic images which each detail the reflectance of landscape features in a different portion of the electromagnetic spectrum. Given that we see the world in color and not just black and white, we can create what is known as a color composite, which is what you see here. To do so, we must assign a Landsat band to each of the 3 primary colors, which are red, green, and blue, that our computer screens can display. The mixing of red, green, and blue by our computer screens create a wide variety of other colors. By associating 3 spectral bands to a separate primary color, we produce what is known as a color composite image. If we choose to display the visible Landsat bands, which are band 4, band 3, and band 2, using their corresponding primary colors, red, green, and blue, the 3 bands may be combined to produce what is known as a true color image. This image should look normal, since a true color composite closely resembles what we would see with our own eyes. We know from previous lectures that vegetation appears green to us because it reflects more green wavelengths than others in the electromagnetic spectrum, in the visible part of the electromagnetic spectrum. We told the computer to visualize band 3, which is the green wavelength, using the green primary color. That's why we see vegetation as green in the true color image. The same can be said about why the water is blue. Water reflects more blue wavelengths than green or red, and we told the computer to display band 2, which is the blue wavelength, using the blue color, so we see the water as blue. So we now know that if we display the band 4 red using red, band 3 green using green, and band 2 blue using blue, we get a true color composite. But what if we choose to display other bands instead? After all, the example Landsat image we're using has near-infrared and shortwave infrared bands too. If we do this, we create what is called a false color composite. A simple way of thinking about a false color composite is that it is any way of displaying spectral information that is not panchromatic, which is just visualizing a single band, or a true color composite. Given that we have 6 bands to choose from and 3 primary colors for displaying them, red, green, and blue, we can start to get creative with how we visualize our Landsat imagery. For example, we can visualize wavelengths outside of the visible spectrum. In this false color composite that you can see, we visualize band 5 near-infrared using red, band 4 red using green, and band 3 green using blue. This means that where you see red, we're seeing a high reflectance in the band 5 near-infrared. Where you see green, we're seeing high band 4 red reflectance. And where we see blue, we're seeing high band 3 green reflectance. This can be confusing at first. The most important thing to remember is that we are displaying wavelengths as colors. No matter what wavelength bands we choose to display, we need to display them as either red, green, or blue using our computer screen. To explain our example a bit further, remember that vegetation is highly reflective in the near-infrared wavelength. In our false color composite, we displayed band 5 near-infrared using red, which is why we see vegetation being displayed as red. We can also see a bluish-greenish color in this image. This means that those pixels are reflecting similar amounts of band 4 red, which is being displayed as green, and band 3 green, which is being displayed as blue. Let's do another example of a false color composite. This time, band 6 shortwave infrared is being displayed using red. Band 5 near infrared is being displayed using green, and band 4 red is being displayed using blue. Instead of displaying band 5 near infrared using red, like we did in the last example, I chose to display it using green. This means that everywhere we see green, there is high near infrared reflectance. Places where we see red is where we're seeing a lot of shortwave infrared reflectance, since we are displaying shortwave infrared using the red color. Notice that there's a fair amount of purple in this scene. Purple is the mixing of red and blue, which are being used to display band 6 shortwave infrared and band 4 red, respectively. This means that locations in the image that are purple are reflecting both shortwave infrared and red a fair amount. So let's do a quick recap. A remote sensing image, such as a Landsat OLI scene, is a collection of panchromatic images, each of which show the reflectance of a particular section of the electromagnetic spectrum. In order for us to display a multispectral image, we need to display bands using one of the three primary colors: red, green, or blue. If we assign the band 4 red, band 3 green, and band 2 blue bands from the Landsat as red, green, and blue colors respectively, we get a true color image, which is how we kind of see the world. If we choose to display bands in any other order, such as band 5 near infrared, band 4 red, and band 3 green as red, green, and blue respectively, we get a false color composite, where areas in red are showing high band 5 reflectance, areas in green are showing high band 4 reflectance, and areas in blue are showing high band 3 reflectance. The ability to display remote sensing imagery in true and false color improves our ability to interpret information and facilitates high-quality spectral analyses.